Okay, so here we are, week 3 instruction, basically going to replicate the lab we did this week, but in R. And so, the first thing you want to do, of course, is get the R file, the week 3 code, and make sure it's on your computer. And again, you have to follow these 3 folders and how I set up the directory structure. You need to do the same. So I put the file here in the code folder. So if that's not ringing a bell, please go back and watch the last week's lecture or supplement where I talked about needing to have everything spelled exactly the same and set up the same because we're using a feature in R called projects, and it's highly sensitive to how you have it all set up. So when you open R, you can work not in a project or you can work in a project. I always suggest you work in a project, and there's 2 or 3 ways you can open your project pretty easily. You can just come up here and click the little down arrow and it'll show you all of your recent projects you've worked in. You can also come here and it's this blue cube looking thing and that will launch the project. So I clicked, I've already opened my project, and now, you can navigate really easily because all the associated files are saved right here in this same file, the same overarching folder that our project is saved in. So here I'm going to click on the week 3 simple linear regression notes. And so I'll say there's 2 parts to this walkthrough. The first part is going to be fitting the same exact model we fit as a class using the states data set. And then there's actually a supplemental part. And I'll talk about that shortly. So, we have a SPSS data set. It's the .sav data, right? States.sav, that .sav is the SPSS file extension. I also uploaded a CSV file. So, typically I would suggest always import a CSV file, and I would usually not import a SPSS data file either. I would go to SPSS and export to a CSV and then just use that. But here, I'm going to show you, suppose you have a data set in a different statistical language like Stata, SPSS, or SAS. Well, how do you actually import that kind of data? So base R does not have a function to import these other kinds of data sets, which means you need to use a package or library that someone else created to do the job. So, all I did here, I had no idea how to do this like 10 minutes ago. I literally just went to Google, I typed this in, and then one of the first links, which I put here, said I can use this package called foreign, which allows you to import other data sets into R. So before you can use the foreign library, you've got to install it. So you only need to do this once. I'm going to run it again. I'll note that if you've already installed something and you run this code again, it's completely fine. It actually just updates it. So there you can see, it's successfully installed. And if you ever want to explicitly check, you can come here to the packages and you should be able, yep, right there, to get some information on the package that's installed. If I had not installed it, you wouldn't see it in this list. Now, I'm going to use a function from this package. This package foreign has many functions that the author created for you to use. One of these is the read.spss file or function, and it allows you to read .sav files. There's also some other arguments here. I think actually in our data set, all the labels were empty, so that's really not going to be that useful for us. To data frame, if you remember last week, I was talking about how a data frame is a particular kind of object that holds, variables in the rows and columns. Sorry, variables are in the columns and observations are in the rows. It's basically your standard data set object. So you usually do want your data to be saved in R as a data frame. And again, I'm assigning this to a thing called df for data frame. So if I just try to run this, it's going to tell me cannot find this function because it's not part of base R. So when you use other packages, you first have to tell R that, hey, in this R session, I'm intending to use these set of functions. So I went ahead and I just hit library, and you can see down here, it basically executed that without an error, so that's good. And then I ran the importing code, and now you can see my environment, it has successfully been imported. Now you have to remember that when you're importing data, it's not like going through a file import menu, which you can do, but typically our users will not do that. But you just need to remember that the file paths that you use, you have to have them exactly correct, right? Just like you would navigating on your directory structure on your computer, you need to tell R exactly where these files are found. So the Git working directory will tell you where R is looking. So if I execute this, you'll see that R is looking in this R labs folder here, which on my computer is right here, same file path. But notice there's no data set there because I've saved the data in this data folder. And so what you have to do then, and notice it's in quotes, the data set name, you can use single or double quotes, it doesn't matter. I've told R to, relative to this working directory path, look inside the data folder. So you can also see it here, the data folder, and then you'll find this file states.sav. So that's how to kind of read that line of code. But going back to what I was saying a few minutes ago, usually I prefer to work with CSV files because any software can read a CSV file into it. So, my CSV file is also in that data folder. And what I'm going to do is I'm going to delete this file encoding, show you. So I imported something called dat, not df this time, but dat. Notice that they have the same dimensions, same variables, but notice the strange name of that first variable. So there's this really useful argument. I would just recommend basically always using this. I'm not really sure I understand what file encoding means exactly. But in any case, when you add this file encoding argument, you'll see that the first variable name is just imported correctly. So in general, when you use the read.csv function, this is part of base R. I would just recommend always adding this. And then, header is whether the first row has variable names or not. Ours does, so we put header equals true. And in case you need to read more information about, how you can, different things you can tell the read CSV function, it's all here. So, you can come and read about header, file encoding and all that. So there you can come and learn about file encoding if you want. But again, I think Googling is just as effective as using the help menus sometimes, because sometimes it's a little hard to understand this stuff. Okay, so we have our data set imported. And at this point, we're ready to fit a linear regression model. Well, I foreshadowed last week, it's really pretty easy. There's a function called the LM function standing for linear model. And how we write the syntax is we put the DV on the left, we put the IV on the right. So here teacher pays the predictor. This is the outcome variable, SAT variable scores. And then I'm telling R where my data is saved. Now, like usual, you can you can highlight and run just snippets of the code. So, here I've got the intercept and the slope, which are the main ingredients of any linear model, right? And I can also store the results using the assignment operator in an object, which I'm going to call mod. So notice I execute this as usual. It doesn't print because I haven't asked it to. And it is now giving me this mod in my environment. And mod is, this is an object called a list. So if you come in here and you run class on mod, well, it's just telling you LM. I guess it's a unique class for just the LM function, but really it's really something called a list. And list is an advanced thing. It can hold all kinds of different data sets and different kinds of information in it. And if you actually click on mod, you can kind of see, you can come in here and get information about what is exactly stored in this so-called data object. So remember, data object is a very, very broad term in R. There's all kinds of objects, data frames. There's a factor for a categorical variable, a numeric vector for numeric variables, etc. So this is the first we've seen a list, but that's like pretty, I would say eventually you'll want to learn about lists if you keep studying R. And it's not something that's so important when you start learning out, understanding exactly what a list is. I think it's kind of a confusing concept if you were to, look into it and read a little bit about it. So I wouldn't worry about it yet. In any case, this mod object, it has stored all the information about our linear regression that we specified here. We call this model specification. And so I can just type in mod and it will just spit out very, very basic information. You know, what is the model? What is the data? And here is the main estimates that we're interested in. Usually though, you're going to want to look at this in a summary table. So the summary table is a lot more useful. You know, it shows the traditional coefficients table. You've got the estimates, the intercept, and the estimate for the teacher pay slope. Notice how it's identical to SPSS. You got the standard error, the t-value, and the p-values. So the t-value is your test statistic or your t statistic. And down here, you've also got some summary information. For starters, we have R squared. Again, it's the same that we saw in the lab this week. We also have our F statistic and our p-value for the F statistic. Remember, this means you're testing for overall model significance. So here, the model, which in this case is just one variable. So you really could just say teacher pay is significantly associated with SAT verbal scores. But you know, next week we'll be taking a bigger look at the F statistic and how to interpret that when there's multiple variables in the model. We also have the residual standard error. Now, SPSS, I think this is called the standard error of the estimate, or maybe it's the standard error of the regression. I think it's standard error of the estimate, but you know, it's the same number, 30.05. So notice our output is all the same. And you know, the cool thing about this is really all you have to do if you're using, you know, you got a new data set or something, you just change the variable names, and it's pretty easy and quick to use regression on any new project. Now, we also looked at, SPSS gave us the model summary or the ANOVA table. So the analysis of variance table, there's a function called ANOVA. And all you do is you put your mod object, whatever you named it. I called it mod here. You just put that as the input to the ANOVA function, and out comes the ANOVA information. And again, this will be the same that we saw in the lab. So just like that, we've actually replicated the main things that we did in the lab. We just didn't talk about interpretations and all that kind of stuff here. So I also wanted to give you a second example, a second simple linear regression example below. So, you know, we're still at the beginning of learning R, and there's all kinds of ways to import data. This is a new one that you haven't seen yet. You can actually import straight from a URL, which is pretty cool. I'm not sure if SPSS can do that, but you can see how simple it is here. You know, it's a text data file that's saved at this URL, and it's just a read.table function that's part of base R. So if I import that, it's going to take a second because it goes online, and you can see right there's my data set, 3 variables. Now, those names aren't very useful, right? V1, V2, V3, we don't know what they are. So let's see. We can change the column names. So I'm going to call the column names function on data. And again, data is the object, column names is the function. If I just execute that, it will just return the column names. But I can overwrite the column names by passing a character vector with the appropriate names. So that's what I'm going to do here. And now you can see I've got my column names. So the DV here is like, how much a respondent liked. I can't remember what it was. Maybe it was a candy or something that they were eating. And then we've got 2 statistics, pieces of information about each piece of candy, sweets and its moisture level. So clearly preferences like here is going to be the DV. The others we're going to view as predictors. So again, you know, one of the first things I do, you don't really need it here because it's a small data set, but if you had a large data set, I usually do like to just look at the first few rows, and the head function in R is really useful for that. Again, like last week, we can look at the dimensions using the dim function, 16 rows, 3 columns of data, and we can see the variable names with the names function. Now, just like last week, we can also do some descriptive statistic stuff. Now, last week, I talked about how, you know, this is how I usually would code it. I would do data as that's where my data is stored. And then the $ like basically highlights one variable at a time. And you can see those values, 194 there, just that first column, right? But let's say you didn't want to type in data $sign every time. There's a function called attach. And what that allows you to do is basically not have to go through writing this data $sign everywhere. It just attaches it just assumes that it's from the data object. That I named data here, so it's kind of confusing. But anyway, that's a cool little trick to save you some time when writing out your code if you want. I will say most R programmers don't do that too much, but it is something to know about because you might see it occasionally. And we can also, of course, use the summary function on the entire data set, and it's going to give us these statistics. We can do a correlation matrix. They're all numeric variables. So R is going to have no problem just spitting out the correlation. So here, you know, like has clearly a strong correlation with moisture, probably an important variable there, right? Also pretty moderately to strong correlation with sweet. And one thing we did in the lab is we also plotted the data. I did show you some code for that last week. So here, you know, just again, running through the code, I described this code last week. So I think when it comes to learning R, you kind of had to get in there, look at exactly what the arguments are, delete them out, rerun it. It really comes to a lot of trial and error is how you learn something like R. So, you know, I gave you a quick introduction to the plot functions last week. So here I've just set up the code for you, and please experiment. That's how you're going to learn R. So this should say a histogram of, so we can, of course, look at a histogram of a variable like this one, which is called light. And, you know, so you see the only difference in the last two plots is that one has a frequency listed, one has density. So density and frequency really are kind of synonymous. Frequency is an actual count. Density is kind of more like it's kind of like a probability number. So it's not quite a probability, but you can kind of think of it as, you know, the probability here is 0.15 being in this bin. Probability here is 0.03. Now the probabilities, it's not strictly a probability function, but that's a way to think about it. It's a little too much detail that I don't want to go into right now. Definitely ask me about density if you're curious about the concept, but it comes from the word probability density function, a PDF. So it's got a lot of mathematics around it. And, you know, I can add other arguments, change my histogram. And then I can even do something like this lines function takes the previous plot and it adds some information over that plot. So here you can see the density plot is kind of like this smooth thing. So when you see a normal distribution, you usually don't see histograms too much. You kind of see it, it's usually as a density plot. It's like a density plot really is like a smooth histogram. And finally, we can, of course, fit a linear regression model. And so just using the same syntax as before, but notice I didn't have to define a data object because I had attached up here. Now, this next part is to kind of just help you kind of still get comfortable with our syntax. So, you know, here, I'm going to go through it pretty quickly, but what we're going to do is I'm going to show you how to actually calculate all the values in the ANOVA table. You know, some people might be interested in the mathematics, not everyone is, but here, if you're going into R, I think there's probably a greater chance that you are interested. So I wrote some of this code to show you how to calculate the different values in the ANOVA table. I remember in the Tuesday lecture, we talked about R squared. It's basically the regression sum of squares over the total sum of squares. So this is the notation I'm using here, reg SS, total SS, total sums of squares, and this is the residual sums of squares. So, you know, going through these and executing these, you get your ANOVA table here. So the residual sum of squares is right there, 400.55. You can see I'm storing that in my new variable called RSS. So it puts it here in the values list. And for the regression sums of squares, You know, the explained variance is ultimately explained by this variable moisture, because that is the predictor here. And so typically, if you had more than one predictor, there's a few ways to show it in an ANOVA table. You could actually show each predictor having its own sum of squares. SPSS by default will just give you the total sums of squares for all the explained variance. It doesn't break them apart unless you ask for it, and there's a way to do that. We're not going to go into that. And I think let's see if I add like here, what is it going to do? I think it separates them with the ANOVA function maybe. What does it say, model? I think well, don't worry about that error. Let's just see if it worked. Okay, yeah, so I don't know why. Let me try. Okay, so there's something a little complicated going on here. I think it's like maybe there's a lot of overlap between moisture and light, and that's why it's doing that. But in any case, when we do multiple regression, I'll set up an example next week, and we'll look at the ANOVA table again. So we'll see there. I think R splits them apart, but we'll have to see next week. So again, you just go through this, kind of get more familiar with it. You can take these things you defined in the previous step, use them to get your total sums of squares. R squared is literally regression sum of squares divided by total sum of squares. So you see there, I have a 0.7963. If I come back up to the linear regression model we fit, notice the R squared is going to be matching what we just computed. And then how do I actually calculate the sums of squares without using any of that information in the ANOVA table? Well, remember the regression sums of squares, it's y hat I, or it's the predicted value for person I, and minus the mean. So that's the regression sum of squares. Remember the predicted value minus the mean, and we did that on Tuesday. So please go watch the video if that's a little confusing. But notice we can actually use the predict function in the regression. So reg is an object, and it's filled with my regression information. So there were 16 observations. So when I run predict, it's going to give me 16 different predictions. And these are like basically all fall exactly on the regression line. So for 15 and 16, we see we have the same prediction, for example, and even 14. It's interesting. I don't know why I keep getting this error message. But let me see if it went away there. Okay, so it's happier now. And you can see if we compute it by literally just kind of doing the math by our hand with R, so to speak, you can see I'm getting the same exact values. So we can also do the mean square of the regression. And you would just divide it by its degrees of freedom. And in the ANOVA table, I think it showed the degrees of freedom. Yes, it did. So I'm dividing it here by 1, which of course doesn't change anything. So the sum of squares and the mean square turn out to be the same value here. And then we can also estimate the sum of squares of residuals. So I'm calling that SSR there. I should actually, let me go back to RSS. And you see when I click on SSR, it kind of highlights it everywhere. So again, you can calculate it by hand. You're going to get the same values as the ANOVA function, of course. And then the mean squared error. So if I do ANOVA reg, the mean square error is here, 28.61. So again, you can actually, it's really just the regression sums of squares divided by its degrees of freedom, which is 14. And here I actually put, like, it's in the lab notes for SPSS, I actually put the full formula. And so it's n, which actually would be the length of however many observations you're using. So here, the length of the like vector is 16. So that's our full sample size minus 2. So we'll be talking more about the degrees of freedom a little bit in the coming weeks. But anyways, you can see we got the same estimate as the ANOVA function. And then our F statistic is ultimately this number, the explained mean square, divided by the residual mean square, or the MSE. And so what I can do is I can show you that we get the same exact F value like that. And then finally, if I want the p-value for that test, I get the same exact p-value here by using, this is a probability function of the F distribution. And then let's see what it's calculating the standard errors. I see the regression. I'm going to delete this. We don't. Well, okay. I think what we just want, calculating the standard, this should say, calculating the standard error of the regression / the residual standard error. So the residual standard error is literally just the square root of the MSE. So 5.3. So if I again go to summary mod, oops. You'll see that the residual standard error is 5.39. Now that should be equal to what we just computed. And so the residual standard error is it's this just a square root of the MSE. And remember, the MSE comes from our ANOVA table right here. So the square root of 28.61 is going to be 5.349. Okay, so that's all for this week. Please feel free to reach out if you have any questions. I think the best way to learn R is really just get in here and do some practicing, try to break the code, try to fix the code. And, it's a lot of probing and patience. But I think after the first kind of big push of about 10, 20 hours, you start to get kind of comfortable with it and really becomes kind of enjoyable because it's kind of a little puzzle every time you're trying to program something and solve some kind of new issue. It's pretty enjoyable for me, at least, to use R. So I hope you guys have the same kind of curiosity when you come and learn this, because I think that's really the key. Always kind of when you start learning something like this, just be willing to make mistakes, troubleshoot your mistakes. You've got me as a resource and maybe some of your peers. So don't feel like this isn't part of the class. I definitely want you guys to learn R if you're motivated to do it. So I know our focus is on SPSS, but please don't hesitate to reach out with any questions you have about R. Thanks, guys.